So here about Fred. He is originally from Connecticut. He was educated at the Polytechnic Institute of Brooklyn and Iowa State University. He was employed by Sandia National Laboratories for 28 years, and he retired in 1999. After that, in 2000, he started his second career as an artist. And because his mother was an artist, participation in art-related activities began very early for him, even though his career as an artist didn't start until 2000. He's attended many art workshops and taken many art classes at different institutions, and he studied with people including C.W. Mundy, Robert Liberace, and Sherry McGraw. And he spends a significant amount of time painting and experimenting with various materials for sources of artistic inspiration, and he's a very active member of the Art League, as I said, as well as the Rio Grande Art Association. So please help me welcome Fred Yost.
You can't do a better job than that. Thank you all for coming. It's really a thrill and a pleasure for me to give a presentation to you. With such a big turnout, it's well worth the work that I had to put in to do it. Because the topic was suggested by Jamie and Dan on the board, and I wasn't quite ready to put the two together, but they fit together better than in your sock. So the title, it wasn't meant to be suggesting that there's two talks. We didn't mean to do that. The word beauty applies to both mathematics and nature. It just didn't work out that way in writing up the title. If you can't hear me, somebody say, louder. Okay. The question somebody is bound to ask is, what in the hell do you mean by the beauty of mathematics? I mean, I had algebra in high school, and there wasn't anything beautiful about it. Galileo said, nature is writing in mathematical language. So mathematics is a language. All languages are beautiful. So the way mathematicians answer that question, what do you mean by it? They use other words than beauty. They say it's brevity, it's simplicity, it's adaptability, it's elegance. All of those words apply to the beauty of mathematics. The same is true for a language. Let's see if I can make this work. This quote, "The beauty of English language lies in its unique properties, quirks, and the comparable flexibility that sets it apart from other languages." Well, there's no beauty in there. It's not like beauty in a flower, beauty in a painting. It's beauty in the quality. It's beauty that you realize after you learn the language. Well, we've all learned English, but we haven't all learned mathematics. Now, you don't need to worry about mathematics. If you haven't had any, I'm not going to test you. I'm not going to make it complex. It's going to be a brisk brush stroke to give you the feeling of mathematics. And I try to make it clear on how it intermingles or convolves with art and with nature. Most of my slides are going to be about nature, about things that are kind of mathematical, like spirals. That's mathematical, but it's also nature.
Thank you so much.
So my outline, I'm going to start 300 years BC with the Greek mathematician Euclid. And he could be arguably said to be one of the best mathematicians of all. He wrote 13 books on mathematics. The first 6 were on plane geometry. The last 3 books were on solid geometry. And he also was the first person to talk about the golden ratio. That comes as a surprise. It was a surprise to me. It felt like doing my research on this. I didn't realize it. He was the first one. Some people say Fibonacci, but we'll get to Fibonacci. But Euclid, we've got to give him the credit, because I'll show you what he did. When he wasn't writing a book like that, which is on papyrus, doesn't exist in totality now. There are very few copies of it. This is just a fragment. Paper wasn't invented then, so they had to handwrite books out. But when the Renaissance came and invention of movable type came about, books were then printed and people could read what Euclid had said many, many years before. And when he wasn't writing this book, he was thinking of a straight line, and where could he cut it so that it was kind of aesthetic. And all Greeks are crazy about aesthetics. It's very important to every Greek, even today. And so he said, what if I set this ratio, the total length of the line divided by the longest length of the line, and set it equal to the longest piece of line divided by the shortest piece of line. It was just inspirational for him, I think. But also he was able to say, let me define this A or B as phi. Then I can talk about ratios, because this equation divides out so that you get this equation, 1 plus 1 over phi is equal to phi, or this quadratic equation. Then, if you have high school background, you can solve that equation. And it turns out to be the golden number. Surprise.
So, Fred, so this seemed like just an arbitrary thing they wanted to try.
Yep.
There was no
Yep.
magic in it.
Exactly. And that short question, what if, seems to precede ideas time and time and time again. Instead of sitting on the couch and say, what if I do this? You might come up with an idea. Okay, but now Fibonacci. We're not going to go right to Fibonacci because we still have a whole lot of time to cover. We're 300 years BC now. But during those years, architects and artists picked up on the idea of the golden number being related to art and with aesthetic appeal. And so they started talking about the pyramids, the Parthenon. And in those cases, you can't measure a building with enough accuracy to compare to the golden number, 1.618, blah, 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 blah. There are too many ways to measure it. But in this particular painting, which was produced in the Renaissance, if you measure the distance between God's pointed finger and this side of the painting, and divide it by the distance from there to that side of the painting, you get something very close to 1.6. 1/8. Surprise. There's so many surprises in this that every once in a while it feels like you get hit in the face with a flat shovel. I mean, that's what happens to me. It's so surprising. It just pops out. Some people like to say that the UN building has the shape of the golden rectangle. Cigarette packs, playing cards, everything has the beauty of the golden rectangle. So not to be outdone, I did a painting several years ago. This is about 30 inches wide, 30 inches tall. 2 pieces divided according to the golden ratio, separated by a couple of pieces of walnut and a piece of aluminum. And the color fields are coated with epoxy. epoxy resin, clear epoxy resin. This is another case where I'm trying to compare my abilities to those of Euclid, and which is a long story. Again, I've got the golden ratio partitioned into this diptych. Oops. Which brings us up to 100 years BC, and this Roman fellow, Vitruvius, he wrote a book on architecture. He was an architect. And he had strong feelings about how buildings should be built, as do all architects. But he also felt that the human body should have all of those attributes: strength, resilience, resistance to fatigue, resistance to weather, and be beautiful at the same time. That brings us up to this fella, Luca Pacioli, another Italian fella. This is his student or whatever. I don't think he's Italian. He has a Roman nose. He's got a nose that's more like German. But Luca had to have read Euclid's book, The Elements. He knew about mathematics. He taught mathematics everywhere in that region. And he wrote this book, Divina Proportione. Also wrote a Latin translation of the Elements by Euclid. So he knew very well what the golden ratio was and taught about it. So now we're going back from 1500 to 1200, and we introduce Fibonacci. Fibonacci was a wealthy guy. He was a merchant, but he also taught mathematics all around the Mediterranean. Lived in Venice a good portion of his time, and Pisa. I should have said one more thing about Pacioli. This guy was lucky. He had some friends that I'll introduce you to in just a couple of slides. So, Pacioli wrote this book, and he needed an illustrator because he didn't like that drawing that was in Vitruvius's book showing the strength of a man. He wanted a brand new drawing. And he had a friend that he grew up with, as it turns out, and lived with as an adult for a while. His name is Leonardo da Vinci. Now there's a stroke of luck. There's a stroke of luck, because Leonardo, of course, did this drawing, now called the Vitruvian Man. And it's supposed to be related to the golden ratio. Well, that's Fibonacci. And what he introduced was this very simple equation. Can you see? He introduced this equation, which is as simple as you can possibly get. You just take two numbers and add them together. You get a third number. It's like a number generator. Okay? You just turn a crank and you get a new number. Keep feeding it new numbers. You get new numbers. And you end up, you have to put in a couple of seeds to start this machine. And you get this sequence of numbers. And people looked at that and said, you know, I've got flowers that have three, what are they called? Florets? What are the things?
Petals.
Petals. There's 3 petals. I've got other flowers that have 5 petals, and still more that have 8. Isn't that a coincidence? Other people say, well, I've got a pineapple that has 13 spirals, etc. And so this sequence of numbers became common to everyone. They had a feeling for these numbers, that it belonged in nature, that it was God-made. And again, this is a flat shovel in the face. Bang! Smack! Now, one of the curiosities here is that if you start off with two other numbers, let's say 15 and 16, you still get an enormous growth of the number because you keep adding numbers. But what's curious is, if you take ratios, like Euclid and Pacioli, not Euclid and Pacioli, Euclid and a fellow I'm going to introduce, you still get growth, but you get a limit, I haven't shown it yet. So I plotted these numbers out. This is what it looks like. You get enormous growth. Now we're talking. These are like the number of times that I've cranked it, like 25 up to this point, and up here is 1 million. So we get rapid growth. But if you plot the ratios, it quickly approaches a limit. And that limit, probably can't read it from where you are, is just a little bit above 1.6. That's the golden ratio. Surprise! Another curiosity, if you start off at 15, 16, 31, and 12, you still get this limit if you look at the ratios. It's not part of having 1 and 1 as your seed numbers. It's unique. It happens for all numbers. So, this fella, Robert Simpson, who was a mathematics professor at the University of Glasgow in Scotland, he knew about this ratio approaching a limit. The calculations that he did by hand showed this limit forming. It doesn't take long before you see it happen. And so he read Euclid's The Elements, and he decided, I'm going to take Fibonacci's equation and divide it so that I have ratios. And then I'm going to do some algebraic manipulation with those ratios, which are hidden behind here, so I'm shielding you from just a little bit of high school math. And out comes the golden number. So here's the golden number popping out twice, mathematically. Once by Euclid and his ratios, what if? And this guy with ratios and Fibonacci's equation. It didn't come out of the Parthenon. It didn't come out of a painting. The architects and the artists have used that golden number for their benefit. They didn't invent anything in this regard. So after this fella, everybody began to notice these numbers popping out in all sorts of ways in nature. The spiral of a pineapple and a pine cone, spirals in the galaxies and hurricanes, horns and shells and fossils, crystal growth, leaves, exoskeletons, and we'll get to some of these. This is where the beauty lies. And stripes on angelfish, stripes on zebra. How do you explain those?
Can you say something about soap bubbles? What's the deal?
You get geometry, you get hexagons. If you're looking in 2 dimensions, you often see hexagons sitting all together, close fitting all around. And if you look at it in 3D, you see polygons also close fitting all together. And there's mathematics that go along with that. And I didn't bother with that to show you. I didn't anticipate the question.
We wouldn't understand the answer.
Come on.
So, not to be outdone, I went to my studio and I painted a spiral. It's called Fibonacci spiral. I'm not sure if Fibonacci ever did draw a spiral knowing his numbers, but other people have since then. And so I had to give it a try. And this is on board with lines that are filled in with black paint and encaustic that has been pigmented in all of the color fields. So spirals, you see galaxies, you see sunflowers, you count up the spirals and you get a Fibonacci number. Fossils, beautiful fossils. I had a chance to buy one of these. It was that big, and I lost it. This is a fossil, a spiral. It's called a latus. There is a whole list of famous spirals in mathematics books. This one, this spiral, is called a latus spiral, and there's an equation that goes along with it. The fiddler fir. How many, you see these things, right? I think they're beautiful. I was surprised to see them. Chameleons. Spirals everywhere. All clay. Van Gogh. And Fred. That's the only time ever since that those three names came together. Well, here's latus. Again, I'm using the caustic. The equation for the latus is up here, which you can't see. It's covered with various coatings. This is the equation plotted out. You can see the spiral, and then it goes off to infinity as a straight line. That doesn't happen with other spirals. They just keep going around. So it's a special spiral. These are collaged on fiddler, a fiddle, and a latus. So one day I said, spirals must be God's favorite shape. I mean, after all, there's so many spirals, and they're so beautiful and can be explained mathematically and biologically. Speaking of biology, we're taking a detour here. This fellow, Eshel Ben Yaakov, used to be a physics professor at Yeshiva University in Israel. His fascination was growth of bacterial colonies. And so he put together a Petri dish and agar gel with water and maybe a little bit of sugar. Stir it all up, let it harden inside the Petri dish. And then touch a little bacteria in the center of this. And you get this. Mathematics. Here we have symmetry. We have pattern. We have repetition. We have rhythm and color. All from bugs. Now, I'm sure you're not all anxious to go out and start this experiment. But it's easy to do. You can go to Walmart and buy one of these Petri dishes with gel and water already in it. Take it home and put some dirt on it. Nobody wants to mess with bacteria. I'm not suggesting you do it. But it surely was enticing to me. I never did it, but I'm still thinking about it. Okay, in the ocean are protozoa. Lots and lots and lots of different kinds of protozoa. And they're filled with protoplasm and cytoplasm and all kinds of other plasms. But when they die, those plasms dry out and they turn to dust, get washed away, leaving a skeleton, a silicate skeleton. That is just plumb beautiful. There's the flat shell. And there's all kinds of these shapes. There's many, many different kinds of protozoa like this.
So in that shell or in the bacteria, you see a very beautiful regular pattern. But do you see the golden number in those?
I don't. I haven't tried
Okay.
because I don't have firsthand I can't put my hands on this.
That was
But-
just brought
but
back
I-
what
yeah.
I was trying to connect.
I haven't read anything about it either. But this talk isn't only about the golden number. Okay, now, because the last few slides were just images of nature, don't think that mathematics, you're done with mathematics now. You're not going to get a test, but I'm going to bring up some other mathematics because it's so it's impervious, it's everywhere. It's a language. In 1902, Rudyard Kipling published his book, Just So Stories. It's a storybook for kids, young kids especially. And there were chapters in it. For example, how did the elephant get his trunk? And that's how Rudyard imagined it. There was another chapter in that book called How Did the Leopard Get His Spots? And I think that chapter, at least, was read by this British mathematician, Alan Turing. Alan Turing played a huge role back in World War II that I'll get to. But he was a crypto analyst, he was a mathematician, he was a computer scientist. In fact, they now call him the father of computer science. But what he did early in his career was to try to build a mathematical treatment or model about morphogenesis, creation of shape, the shapes of spots on the leopard, or the shapes of stripes on his. That was his goal. And he wasn't into biology. He didn't know biology. And so biologists criticize his work because it is totally lacking of biology. But they also give him credit for at least making a stab at how do you explain this spot and stripe formation. He did a great deal of work in the starting of this subject called morphogenesis. The approach he took involves mathematical equations called reaction diffusion equations. Now, I've had some experience using those, working on solving those equations for a morphogenesis problem. That being, when sometimes crystals grow, they grow in the form of a thin platelet. Other times, they form in the shape of sharp needles. And there's a transition. You can get one to grow or the other to grow depending upon the conditions of the growth. And so there is such a thing as a plate to needle morphological transformation. And if you Google that, you'll find my thesis somewhere along the line. But the other thing he did, he's much more famous for, is to crack the Enigma code. During World War II, the Germans manufactured this machine called the Enigma machine, and it was used to send codes to their various army groups all around the war front. And I don't know for sure how this works, but let me take a guess. You have what looks like a typewriter keyboard right here. If you want to send a message, let's say ABC. Well, A, you press the A key, and this has a random number generator. Let's say it has 6 figures in it. It gives you a random number that forever, for this message, stands for the letter A. And then maybe there's no space, so you just go on to the letter B. But if you want to make a word, you need to have a space. You need to have a code for that space too, otherwise someone can't read it readily. And so it's a random number generator. And once the other guy gets it, he knows it's a random number generator, and he knows that it corresponds to a letter A, etc. So he can read the code. Well, Alan Turing broke that code as a British member of the military. And that's how he got famous. Not to be outdone, I built these two cradled boxes. They're built like a cradled box. They're trapezoidal rather than square or rectangular, but they serve well. I prepared also using those clear plastic bottles you can get at Walmart, and it has a spout on the top. You can put ketchup in it, and you can squirt it. I put paint in those. I had enough of these bottles that I could put any colors that I wanted in there. And I made it so that I could pour it through that fine tip. And what I did here was mix it with clear varnish to make it more of a liquid. Let's say oil paint out of a tube with clear varnish will become a liquid if you mix it up. Put it in the bottle. Black in this case and white in this case. And prepare the boards. Make sure they're absolutely flat. No tilting. Because you pour a liquid on a tilt, it's going to run off to the side. You don't end up with a painting. So it's got to be absolutely flat and preferably smooth. Then you start pouring your paint. People in here have heard about pouring paint. Well, this is my attempt long before acrylic pours became all the rage on YouTube. I had a fun time doing it. I did a whole series of these kinds of things. And that painting is going to be in, I think it's the next show, Out of Bounds, I think it's called. It'll be in the next show. Here's my attempt at an acrylic pour, because I found this on YouTube. It's all over. Everybody's pouring acrylics. And it's crazy. It's beautiful patterns, and it doesn't take a whole lot of talent, at least on my part, to mix up some colors and pour it out on a flat surface. And you get beauty. Every once in a while, you need to throw one away, I suppose. But look at these. I got these off the internet. They're beautiful. There's no wonder that everyone's trying it. I tried it. I did, 8 of them or so. And not one of them sold. Here's another of mine in oil paint and clear varnish. I just prepared 4 colors and just randomly put them on the surface until it started running off the edge of the board. All of these poured images that I just showed you have been explained from 2 great British physicists, Lord Rayleigh and G.I. Taylor. They're all dead now, of course. But it's pretty simple what they argue. Let's say you take a layer of less dense paint and cover it with a layer of dense paint, heavy paint. Well, the heavy paint is going to want to sink, right? Well, it can't sink in its entirety. It doesn't sink as one fell, bloop. It forms little perturbations. There's a little wiggle in the interface between black and white. And that perturbation grows until you got a droplet that goes to the surface. And then it might spread, it might not. But that's been explained by mathematics. Here's a fun mathematical thing. If you have mathematical software at home, you can do this. Everybody knows that the equation of a circle is x squared plus y squared equals 1. 1 is the radius squared, which is the radius of 1, whatever the units are. But a French mathematician whose name is Lame, L-A-M-E, with a diacritical mark above the E, I think that changes the pronunciation from lame to Lame. He said, what'll happen if I change the 2 to an n, where n is not specified at this point? Cool question, because of what pops out. Suppose we take n equal to 10. That's the equation plotted out. It's a rounded square. Now, as you make n bigger and bigger, starting at 2 and make it bigger, the circle turns into this kind of rounded square shape. Not to be outperformed again. Fred did a painting where I started with a circle and ended up with this rounded square. This was like 1990, 1995. I've been around quite a while. Boom! Fractals. Everybody knows about fractals, right? It's beautiful also. It's purely mathematical. But it's beautiful at the same time. Why is it beautiful? Because he can do it at such a fine scale. That's one. And fractal shapes have a property of shape preservation. This shape is the same as that shape, it's the same as that shape. The only difference is the scale. That's characteristic of every fractal. Fractal approximations by artists can't get that far, nor would you want to. You don't have the skill to get that down that detail. Only the computer does. Here's a fractal-like thing, broccolis. Well, it's shape preserving. Look, I don't know what these. Let me call it a bud. There's a broccoli bud, but here's one also, smaller and smaller and smaller and smaller and smaller. Shape preservation is characteristic of fractal. A leaf. That's a leaf. This is a leaf. This is a leaf. This is a leaf over here. Shape preservation. Dendritic growth, tree-like growth, needles. Shape preservation. Big needles, smaller needles, smaller needles. This is how you build one. This is the essence of a fractal shape. You start off with a triangle. You pick a smaller triangle and place it in there. A smaller triangle, and if you wanted and have the endurance, you can make even smaller triangles until you fill up the whole space with triangles. You can't do that by hand. Well, mathematics gets continued on. Not only do we have Fibonacci equation, but we have a Fibonacci equation in which this guy decided, I'm going to add 3 numbers, not just 2. And I'm going to add 4 numbers and 5 numbers and see what happens. What if? It's the what if question this guy asked. Other curiosities that you run into in reading this advanced Fibonacci literature, which continues today, a journal started in 1963 called the Fibonacci Quarterly. You read these papers and you're blown away by mathematics, so don't even bother going to the library. There's such things as negative numbers. There are things called Fibonacci words. I read that and I said, Fred, you don't have time to walk into that angle. You got to talk to the deliver for the board.
Do you have time to explain how it would work, a Fibonacci, for example? If are you doing 0 plus 1 plus 1?
Yes, you need 3 seeds.
Right.
That's up to you. You can use 0, 1, 2, 3. You can use 1, 1, 1. You can use 16, 15, 23. You get different results.
Does the golden ratio?
Good question. No, you do not. I know because I worked out the Fibonacci. You get 1.8, 139, something like that, and yada, yada, yada. This one's higher than 1.8, and higher, and it's as if it's approaching 2. 2 is 2 squares. It's not a spiral. It's not a rectangle. It's not a triangle. But that was curious. That was interesting for me to find out. You know, you have the pleasure of seeing different numbers go to the same limit in the Fibonacci example. But all the rest of them don't. They approach a limit, but they don't approach the same limit. Now, whether you try different seed numbers for those various other Notchis, I don't know. I don't know if you get the same limit that you get for your very first choice for the seed numbers. If you go from 111 and then change it to 29, 31, 64, I don't know if you're going to get the same limit of 1.8, yada, yada, yada. That's
What is the Naganesian numbers?
what?
The last 2? What are they?
Neganacci.
Yeah.
That's you pick negative numbers. And that,
Oh, okay.
there's somebody that's studying this.
And if they're negative, do you still get the golden rule if you're using the right?
I have no idea. I kept telling myself, Fred, don't go any further.
Okay.
Because this is just coming up with this talk is enough. Believe me.
A lot of people with spare time on their hands.
Well, I am retired.
Next lecture.
Yeah, right.
Must be a lot of rabbit holes. Hey,
Well-
there's the rabbit.
Well chosen words. Albrecht Dürer, you probably have heard of him, at least from his painting on the rabbit. Did you know that he also loved mathematics? Here is one of the Platonic solids. Here's something called a magic square. Now, you know about magic square? Imagine a checkerboard with 4x4 squares inside. Into each one of those squares, you put a whole number. But you do it so that when you go across a row or up and down in a column, you compute the same number. Each and every row and column comes to the same number. You have to be pretty sharp to pick the right numbers to do that, but it's done many times.
Sort of like Sudoku, actually.
I don't do that.
No.
My daughter used to do it a lot.
Yeah. A final example here that Dürer played with, it's more of just a graphical construction. I think he had fun doing. He called it ein Mussolini, which is German for a shell curve. A shell curve. So not to be outdone, Fred made a clamshell, and he put his own lines on this clamshell.
This sculpture,
Yes, this is three-dimensional. It's about this wide. But it hangs on a wall. Okay, brand new idea here. Most of what we've been talking about have to do with flowers, vegetables, weeds, animals, bugs. But that's not the whole scope of nature. Nature is way wider than that, right? This guy had an interest. Perhaps he was a skier, I don't know. Hernan Maxa, professor of physics at City College of New York. And he was interested in avalanches and landslides and the formation of sand dunes. How do they form? They're not constructed by humans. It happens. And what happens when it's going on? And can we model it mathematically? Because we might be able to save lives if we can do that. So he built what is now called a Maxa cell. Now, this is mine. I built this one. It consists of two plexiglass sheets spaced equally apart by this wood frame. The plexiglasses are the same size. And now what you do is you go to Petco and you go to the fish department. Because in the fish department, they sell stuff that goes in the bottom of the fish aquarium. Like little sculptures and buildings to entertain the fish down there. Well, they also have gravel, sand, colored sand. The most important thing, as Max has pointed out in his papers, is you need two different sands that differ in sift size. Bigger sand particles than another, smaller sand particles. So I bought two different colors of sand that have two different sift sizes.
they actually sell them by size. I mean,
No, you could see the difference. You can also go to a store that sells pumice in different grinds. But what you do now is you take these home and you put them in a big bowl, you stir them up, you shake them up, get it all thoroughly mixed. And then you pour that mixture into a pouring pitcher. And you go to that corner of the cell and you start pouring these sands into the cell. And you end up with this stratification. automatically.
That's cool.
It takes no talent. It's like pouring paint. It's fun to do, and it ends up wondrous. And this happened in my first pour.
Did you try others?
No, I was satisfied at that point. Mathematicians. They're a great group. They love their field. You can't take it away from them. They have achieved a whole lot in terms of helping humanity and understanding the world. But in order to get to the top of their game, they have to acquire confidence, okay? These guys are very, very confident. They ask the question, what's your favorite equation? What's your favorite equation? And so they ranked them all out here. Now this, to me, sounds somewhat infantile. It's sort of like, what's your favorite color? But it's interesting to see what equations pop up. So not to be outdone, I chose the very first one there. And that's what it looks like. The painting is right over there. You can come up and look at it. But these numerals and letters and the equal and plus sign are made out of sheet steel. And so if you ask, why is this equation beautiful? I can tell you it's not because of the sprinkles. It's not because of the gold leaf. It's not because of the value contrast. It's not even because of the cherry on the top. It's because these are the two most important integers in our world, two of the more important alphabetic operators, two of the most important irrational numbers, pi. Dave's wearing what pi is on his shirt. And
We're coming to a nerd conference.
And the letter E. Now, someone's going to say, what is E? Well, I just so happen to have a book over here. If you want it, you can take it home. It's called The Story of E. And the flagged page shows you exactly, numerically, what E is. But you also learn the value of the letter E. And also we have an imaginary number. How about that? Well, this is a plasma cutter that my son-in-law has, and he cut out those letters for me, letters and numbers, and I pasted them onto the board there. Oops. Oh, skipped one.
You have to hit play in public.
Okay, it's okay. We're not missing much. So, thank you so much for coming and listening and enduring it all with me. And finally, let's thank Jamie and the board for making art great again. Pardon me for getting nervous. But it's been a long time since I spoke to such a large crowd. I have other things up front here. I have a tool. If you don't want to find the golden mean for yourself on your canvas, you can use this tool. It's ridiculous, but I brought it along for the humor. I also have a copy of Just So Stories. It wasn't one that I had when I was a kid, but one that my daughter gave me. I have the book on E. I have a book that I used throughout graduate school called On Growth and Form, which is a beautiful written book and one of the first attempts at bringing mathematics and science into life. Any questions? Yes?
Okay, this may be a stupid question. I understand the formula for Fibonacci. I understand the proportions for the golden ratio. But how does it get plotted to make a curve?
It's spelled out.
You make a calculation and you write down the numbers, right? and you make it again. Now you don't have to provide any more seed numbers, you've already done that. It's generating its own numbers. And you keep plotting that number that pops up.
Oh, so you're just plotting the, okay.
Yeah, you just plotting points that you've calculated. And you'll get to a point where it just goes boom.
Oh, okay, thank you.
Yeah.
But for the spiral, you're adding an angular dimension.
The spiral.
So
Yes,
so when you're-
because the golden thing is flat. But if you pull it out from the first one to the second one to the third one, you're going around like this, and then you have a spiral. You're making it three-dimensional. Right.
If you look at a pineapple, you can see spirals, one going one way, going the other way. And if you use a Sharpie pen and mark each one of them and count them, you'll end up with Fibonacci numbers.
So just kind of going off of her question, if you plotted the Fibonacci series on, an XY, you would show the exponential growth.
No. Oh, yes, exponential. Oh, it's not exponential growth, but
Not exactly, but you would
it's
see
rapid.
that. But then in order to turn that into a spiral, you're adding.
If you want to
the first one
draw-
this way, the second one that way, the third number
If you
this
want to
way.
draw the Fibonacci spiral, you have to think in terms of rectangles that are shaped according to the golden ratio. And you start off with a small one, you put it on the page. Then you pick a size that is bigger than that small one so that it fits. And you keep doing that bigger. Rectangle, and you'll generate this spiral.
If you Google it, you go to YouTube, it shows it very clearly.
Yes, you raised something that's very important. This stuff is all over YouTube. It's all over. You can read about Fibonacci forever. There's so much out there. Any more questions?
DNA is
Nothing here.
Sorry? Yes.
What about like prime numbers? Are there?
Prompt numbers,
Prime numbers.
prime numbers, what about it?
Well, are there like examples of where that appears in nature?
I haven't studied prime numbers. I think I know what they are. But I don't, there are theories about them and how they occur. But I don't know very much about them other than that. But if you go to Google, or YouTube, or to the library, the way we used to, you'll find out more about those prime numbers. There are other numbers too. There are Lucas numbers that are very close to being Fibonacci numbers. And there's a whole mathematics involving Lucas numbers that mathematicians have built up through the years.
Have you read J. Hambidge
I have,
on the rectangles?
yes.
Okay, on various rectangles. Well, that would be a good source for somebody who wants to know how to construct them, because he shows you exactly how to construct
Yeah,
in 5 different types of rectangles.
yes. Thank you.
who was it?
J. Hambidge. Hambidge.
Thank you, Fred.
Thank you again for coming.
Thank you so much. A lot of work.